introduction of the kind of random graph models that we'll be interested in. I already preluded a little bit about this and discussing preferential attachment model in very vague and general terms. And now I would like to make that a little bit more precise and also explain where the power laws in the degree distribution in that model come from. There's actually a beautiful argument that that actually applies rather generally and gives very sharp and nice bounds. After that, I will also describe very briefly 5 or 6 related models that have been invented in the meantime, explain from the application perspective why people have been interested in those, but I will not discuss them any further. But it's just to indicate that, you know, I'm focusing on 3 models. There are way more models out there. And actually, one of the things that we don't know is whether all of these models behave in a similar way or whether they're completely different. Okay? So there's lots of questions in that direction. All right. So preferential attachment models. I already showed this, this slide. In a certain sense, around the time of 1999, there were 2 competing groups that both came up with networks and their analysis in real-world networks, and these papers at the time really made an enormous splash and gave rise to an enormous research effort, not just in mathematics, but also in physics, in computer science, in biology, in lots of different fields, social sciences, and so on. And one of these papers is by Albert and Barabasi. And one of the reasons why this has been such an influential paper is that they were the first to look at the degree distribution and to see that these are heavy-tailed in one way or another. And the second thing they did was that they proposed a model that would actually predict these power laws. So this is in 1999. The paper is interesting, although it's not a math paper. You should bear that in mind when you read it. So for example, if you read very carefully, the model is actually not defined because it's not really clear what is happening. On the other hand, they must have known what is happening precisely because they were able to do large-scale simulations. Now, one of the things you need to do when you do simulations is know very well which model you're simulating. So they apparently had the rules in their head, but somehow it didn't really come out very properly on paper. And there's a quote in the rigorous paper by Bela, Oliver, Joel, who were all here, and some still are here, and Tuznadi in 2001, who actually proved what Albert and Barabasi were seeing in their simulations. And that's part of what I'll be discussing today, so the occurrence of power laws. Now, you see a slight difference in numbers of citations, Google Scholar, between the paper that everybody in the applications cites to, 30,000. So this says that there's at least 30,000 papers on, let's say, complex networks from all various perspectives. Clearly, these are not all math papers because we don't publish that much. This really is an enormous number. So it says something about the big splash that this paper has made, even though you can argue that there's insufficiencies in there as well. So Bela, Oliver, Spencer, and Tuznadi really defined the model properly and then also analyzed it. And there's a sequence of papers not just analyzing the degree distribution, but also various other properties. Now, interestingly enough, and this of course happens much more often, there's a new idea in 1999, and then people look back in the literature and they say, actually somebody already had this idea in 1925. And then somebody else had that same idea in 1955, wrote it down again, because, at the time, he writes something like, at the time of the writing of this paper from 25, the whole theory of stochastic processes wasn't sufficiently developed. So he sort of redid some of the analysis. So what is the whole idea behind preferential attachment models? Well, we have a dynamic graph. So it evolves. It evolves in a very simple way. At every time step, one vertex is being added to the graph. It has a few edges to give, and it gives that to the population in such a way that vertices with a higher degree are more likely to attract these edges. So somehow this is sort of a very caricature picture of social dynamics. You have a newcomer in town. he or she starts walking around, he or she is more likely to interact with people who are very socially active and therefore have many friends, and therefore is more likely to get to know this person. So there's some biasing, some preferentiality. And that apparently can be a reason for observing power laws. Okay? So this is sometimes called the rich get richer model, because, you know, if you're rich in terms of social connections, in terms of your degree, you're bound to become even richer. So this certainly is a part that, a phrase that we know from the real world. There's lots of newspaper articles writing about sort of the 1% richest people in various societies who only get richer. Even in the Netherlands, this is happening. But in a certain sense, this is not the right word for this model, I would like to argue, because actually it's the old get richer model. Because it's the initial vertices, the people who were there from the start, that are getting the richest. So maybe this is also true in societies like Microsoft or so. If you were an employee very early on, you're now terribly wealthy. So this is also something that we certainly see in the real world. All right, so what is the model like? Well, I'll use a slight adaptation of the model studied by Bela and Oliver and the others, in the sense that, and even Albert and Barabasi, in the sense that I'm not only allowing for what is sometimes called the proportional rule. So the rule is that you're connected to vertices in a probability that is proportional to the current degree. But I add a little twist to that, a little constant. That's this delta here. So delta is just a parameter. So the game is as follows. You have a newcomer in town, vertex t+1, enters, and he has m friendships to give. M is a parameter of the model, and he just chooses these m individuals that he gets to know, his friends, initial friends, with a probability that is proportional to the degree plus a constant. That's what he does. Now, since everybody comes in with the same number of edges, it means that you can actually compute the probability of attaching to all the individuals exactly, because that's going to be that number divided by the sum of those. Now, the delta I can very easily sum, and it's vertex n. So the delta I have to count n minus 1 times. And then the sum of this is also known because everybody comes in with degree m. So in total there's going to be 2m. The sum of the degrees will be 2m times the number of vertices. Right? So the attachment probabilities are relatively easy. Okay? And in particular, this is something which is deterministic. If you were to take a square root of the degrees, for example, you can still write down a formula like this, but the bottom of the fraction will not be deterministic. That makes life much more complicated. These models have also been investigated. So I haven't been very precise here, and neither were Albert and Barabasi, about how these edges are connected precisely. And there are several ways how you can do it, and all of these have been investigated in the literature. So you could have that the m edges are attached independently, conditionally on the current graph. Or you could say, I attach them, and then I intermediately update the degree distribution. And then I attach the second one. I again update the degree distribution. I attach the third one, etc., etc. These are all legitimate choices. You could allow for self-loops. Here I wasn't. You can disallow self-loops. And all of these different choices have been considered. And in the long run, in terms of the degree distribution, they don't matter at all. So I will just stick to this particular model. But bear in mind, they're different choices. And in some cases, it actually does make a difference. For example, the precise distribution of the maximal degree in the graph, which has been analyzed as well, will depend slightly on the precise rules that you're enforcing. But the degree distribution as a whole will not. Okay? So what I will show today, or at least argue, is that this dynamics will give rise to a power law degree sequence with an exponent that is given by this 3 plus delta over m. If delta is 0, you always get 3. 3 plus delta over m, and since delta needs to be larger than minus m, otherwise these probabilities might actually become negative. That's not a good sign, so delta always has to be larger than minus m. And by taking it to be any value larger than minus m, I can achieve any value in between 2 and infinity. Okay? So on Monday, we were already seeing that this range in between 2 and 3 is special because there you have finite mean degrees, which of course here is obvious. The mean degree is 2m. Sorry, yeah, 2m. So you will always have a finite mean degree, but you will have infinite variance when this parameter delta is negative, and therefore the power law exponent is in between 2 and 3. And that basically means, so delta is negative. What you should think of is that the average second moment of the degrees tends to infinity in probability, or almost surely. Right? So on average, the second moment is infinity. Just like it would be for a configuration model if you choose the degrees to be IID with a power law in between 2 and 3. And this is basically the law of large numbers of some sort. Oh, and this should not be infinity. This should be minus m, 0. So for delta negative, you have tau in between 2 and 3. And for delta positive, tau is larger than 3. And in that case, this sum will actually be finite. This will converge to some constant in probability. Okay? So that's what you should bear in mind. All right, and this is a simulation of one of these graphs and the degree distribution that belongs to it. And one of the things, again, in log-log format. And this looks a lot like what you were seeing in real networks. Again, you have something which looks a bit like a straight line here early on, and then it tapers out a bit widely further on. That's what we see in real-world networks. That's what we see when we have IID degrees in the configuration model, and that's what we see here again. Bear in mind, of course, that the degrees here are not independent. They're highly dependent. Okay? So here you really see the power law in action. Okay, so Barabasi is, I mean, one of the reasons why he's cited a lot is that he's notorious for making big claims. So let me read out one of his big claims. The scale-free topology is evidence of organizing principles acting at each stage of the network formation. No matter how large and complex a network becomes, as long as preferential attachment and growth are present, it will maintain its hub-dominated scale-free topology. Okay, so does everybody understand what is written here? Okay, so let me say something here. Hub-dominated means that the vertices of very high degree play a very important role. The vertices of very high degree are called hubs. Hubs are sometimes also used for other things. Here, in the complex networks literature, if you read hub, you should really think of, let's say, the maximum degree vertex, or one of its sort of close friends. So these hubs play a very important role. Scale-free topology actually means that your degree distribution will obey a power law. So that's the scale-free phenomenon that I've been talking about before. Now, of course, I mean, we've already talked about preferential attachment, and preferential attachment models have growth, of course. But I would argue that this is an oversimplification of the truth. And let me try to argue why. I mean, what we see here is that this linear, or sometimes called affine, preferential attachment function is crucial. Right? We immediately see that the tau is actually given as a function of this parameter delta. Now, if I were to take a square root, for example, then I'm not going to get a scale-free topology. And of course, he's never here saying anything about being affine. Right? With the square root of the degrees, you still have a preferential attachment model in the sense that vertices with a higher degree are more likely to be chosen. But you're not going to get power law in the degree sequence. You're going to get stretched exponential tails. Now, I think Joel last week already talked about what happens when the power is larger than 1. Then you actually get one of these vertices that is enormous. So that's, again, it's not a scale-free topology. So there's something to be said here. It's a simplification of the truth, but there's some truth in it, possibly. All right. Now, I would like to highlight a little bit of the proof of this fact, because actually the proof is interesting, and the proof is beautiful. And contains two key ingredients. One very cleverly chosen martingale, a dupe martingale to be more precise, and a concentration estimate on this based on Azuma-Hufding. And that's already in the original paper sort of from 2001. And then in order to link this martingale to the degree distribution, what you would have to do is also look at the expected number of vertices at time t of a degree k. And you need to analyze this rather precisely. And that can also be done very nicely. So I would like to highlight these two aspects. Okay, I'll just start writing over there, and if my board is up, then I might actually raise the slides. Okay, so let's do the first thing, the martingale. Okay, so I've already written down what the martingale is, and you should bear in mind that it's a martingale in n, not in t. T is fixed, t is large, and n runs from 0 to is a martingale. That's basically the Tower property of conditional expectations, for those of you who have heard of this. Okay, you get more and more information of Mn as time proceeds, but somehow, on average, the information averages out. And another thing that you can see is that if I look at time 0 for this, then I get the expected value of nkt conditionally on PA0. But PA0 is empty. There's no information in the graph at time 0. So this is just the expected value. Okay, so that's actually nice. It starts with something that, hopefully you'll be able to analyze. Of course, the nkt itself is a random variable. That, of course, makes it much harder. Expectations tend to be easier to analyze. So that will be the second step. Okay, so that's the first thing. And the second thing, of course, is that if I take n to be t, well, then I'm conditioning on the preferential attachment model at time t, which I indicate by this. But then I have all information. So that's just going to be nk of t. Okay? So the starting and the ending point of this martingale are actually very nice. And these are precisely the things that we would be interested in. So let's see whether we can bound the one-by-one differences. That's typically what you do if you want to use Azuma-Hufding. So let's look at Mn minus Mn minus 1. And the beautiful and rather striking result is that this can be bounded very easily, and it's almost surely bounded by 2 times m, which is an excellent bound. Okay? How does this come about? Well, let me write this difference down explicitly. That's an expectation. It's always of the same random variable, but I'm conditioning on more or less information. In the first, I'm conditioning on more information, and in the second, I'm conditioning on less. Now, one way to do this step, of course, I mean, it's nasty to subtract off two conditional expectations with different conditionings. So I would actually like to make the conditionings agree. And one way of doing that is by introducing a new model in which the dynamics is exactly the same as this dynamic up to time n minus 1, but starting from time n minus 1, it's completely independent. Completely independent of everything else. But conditioning on the graph at time n minus 1. Okay? And since the next step in PAN is going to be completely independent of what I'm doing to the sequence of random variables, I may write n here, because the extra thing is not going to give me any information, but then I should change this object by putting a prime here, indicating that this is the number of vertices of degree k at time t, where I run the PAN, the regular preferential attachment dynamic up to time n minus 1. And from time n minus 1 onwards, it's a completely independent dynamics conditionally on PA of n. Okay? This is much nicer. Why? Well, now I have the same conditioning, but I have a difference of the random variables. Okay? conditionally on PAN. Okay. So what is then the next step? Well, what is the difference between these two? Well, if I haven't touched the vertex in my nth step, in either of the two dynamics, then the probability of that vertex having degree k at the end of the game is going to be identical. So those don't contribute. So it's only those vertices that I've touched in this nth step, either by the independent move or by the determinist, the PAN move, that possibly might be counted here and not here, or vice versa. But I only have 2m of those. M are touched by the PAN, and another m are touched, at most, by the other dynamics, which is completely independent. So this says that this random variable, even in absolute values, is bounded, sorry, this random variable in absolute value is bounded by 2m. I write this out in all detail in the book, but this is sort of the level at which it was done in the very first paper, and it's basically correct. You have to be a bit careful in writing it down. So that actually means that this martingale sequence is rather nice because it has bounded increments. And then it also immediately means that if you look at concentration of this martingale, Azuma-Hovding will give you a very good bound, because Azuma-Hovding is going to tell you that the probability that MT minus M0 is greater than or equal to some A, yeah, that's bounded from above by Azuma-Hovding by 2 e to the power minus A squared over 2 times the sum up to t of the bounds in the displacement, in the bound on the martingale differences. And these are constant. So this is 2 e to the power minus A squared over, this is 2m squared times 2 is 8m squared. Very explicit. So if I take A to be, let's say, well, the square root of, let's say, 10m squared log t times t, then this is going to be minute. It's small O of 1 over t. Oh, yes, absolutely. There's a t here. Yes, very good. Yeah. And of course, the t needs to be there, because if we do this for IID, I mean, it's a central limit theorem type estimate, right? So if I now take A to be very large, and here I do take the square root of t, which is going to cancel this one, so here I will have e to the power minus some large constant times log t. That's going to be very small. So that actually means that with very high probability, m of t, which is nk of t, minus its expectation, is going to be bounded by this constant times the square root of t log t. And you should bear in mind that if for small k, we believe this to be of the order t. So this really is a tiny fluctuation. And this is completely uniform. I haven't even used what k is. It's true for every k. If you take your constant sufficiently large, with high probability, it's true for every k. So this is a wonderful estimate. Now I'm gone with all of my randomness. From now on, I'll be dealing with the expectation, because of course I still need to know what the expectation behaves like. But I don't have to consider randomness anymore. Any questions about this? So how about the expectation? Well, the expectation is purely deterministic, but still, you need to argue how it behaves. And here I'm going to take it slightly easier. B. I'm only going to take m as 1. You can do higher m's as well. It becomes a little bit more messy. It's not at all more difficult in any way. Okay? So what I'll be interested in is in the expectation, in the recursion relation in T for this expectation. So I'm going to be looking at something like this, and I want to relate it to the expectation one time unit earlier. Now it's helpful here to condition on PAT. And then later I can take the expectation and really get the expectation. Okay? But this is nice because now you can actually compute precisely what is happening. What is happening? At time t plus 1, one vertex comes in, it has degree 1. M is 1. That I should count. That's one term. Okay. Now, what happens with the other ones? Well, you know, most of the vertices that had degree k at time t are still going to have degree k because I'm only adding one edge. So it's actually helpful to write this as a conditional expectation of the differences. Okay. So this one, if I take expectation, I actually get the difference in expectations. This one I can analyze exactly. Why? Well, there's two things that can happen. I'm adding my extra edge to an old vertex. I could choose a vertex of degree k, and then it will get degree k minus 1. I wasn't counting it before, and now I should count it. That actually has probability precisely k minus 1 plus delta times the number of such vertices divided by the probabilities, which I think I argued were t times 2m plus delta. Okay? So that's, you increase, oh, this should be nk minus 1. I attach to a vertex of degree k minus 1. I could attach to a vertex of degree k, and then I actually lose 1. So that comes with a minus sign. Then I have a k plus delta nk t divided by t 2m plus delta. Okay? Okay. So now I'll go there, and I'll take the expectations. And to save me from writing lots of stuff, I'm going to be defining nk bar of t to be just the expectation. And then what I get there is n bar k of t plus 1 is n bar k of t plus k minus 1 plus delta nk bar of t divided by t times 2m plus delta, which I was writing there, but m was 1, so that's just 2 plus delta, minus k plus delta t 2 plus delta, and this has an nk minus 1, nkt, plus this indicator. Now it was not, I mean, I want to show that this n bar is actually very close to t times pk. So what I would like to do is actually subtract that off. Okay, so I get n bar k t minus pk times t. And that's going to be the same as nk bar t minus, oh, t plus 1, t times pk, plus, I still have this 1 pk, because here I have t plus 1 and here I have t, and then I have minus k plus delta over t 2 plus delta nkt plus, plus k minus 1 plus delta t times 2 plus delta nk minus 1 bar of t plus this indicator. All right? So this is just writing. I get a very nice linear equation. Now, pk satisfies an interesting recurrence relation that actually looks a lot like this. So pk is actually the same thing as k minus 1 plus delta divided by 2 plus delta p k minus 1 turns out that there is a probability distribution that satisfies this, and you can compute it explicitly. You can basically bring the pk to the other side, divide through, then it becomes a recursion relation that relates pk to pk minus 1, solve it. It will give you ratios of gamma functions. I will not do that here. It's only this recursion relation that is relevant for me. Okay? Why? Because now I can stick it into that equation, t plus 1 minus t plus 1 pk is, well, the first term I'm just going to keep on having, and then I have the k minus 1 plus delta divided by 2 plus delta t nk bar t minus t times pk, because that actually comes from this term, plus, or minus, k minus 1 plus delta divided by 2 plus delta t n bar k minus 1 t minus t pk minus 1. That comes from this term together with the corresponding term there, and the indicator is dropped out. Okay? So now I have a linear relation between the error that I had first, the error 1 time unit earlier, the error 1 time unit earlier divided through by t, that's actually very helpful, and the error 1 time unit earlier at a different k. And actually, what you can do is you can look at the supremum overall k of this difference. Let me call this epsilon k of t plus 1. You can look at this difference, and you can use this in order to see that it's decreasing. Because somehow the operator that acts on it, which is, I've done something wrong. Yeah? The operator that acts on it is a contraction. I've done it the wrong way around. Because somehow I'm subtracting a little bit more than I'm adding. And that allows you to show that this object, but just by induction, decreases. It starts out being some value, I don't know what it is, but some constant. It actually allows you to show that this is bounded by a uniform constant. So I was looking at the expected number of vertices of degree k. I'm subtracting from it t times the asymptotic degree distribution. So that's both quantities act on a scale t. If I take this difference, I get something which is uniformly bounded in t and k. Pretty nice. Now, that is enough to actually complete the proof. I don't do this precise induction argument that shows that this is bounded from above, but it's not very hard to do. Because actually you can take these two pieces together, then they will come with a coefficient that is larger than 1, because you know k is something which is bounded and t is extremely large. This coefficient is always also bounded by 1, so you can take this supremum and bound it from above by the supremum here and the supremum there. And actually the constants that these different suprema will have, you can add them up, and if you add them up you get something which is strictly smaller than 1, because precisely of this minus 1. This is going to cancel with this term almost exactly, except for the minus 1. So you get that this supremum is bounded by 1 minus something of the order 1 over t times the previous value. Well, that you can iterate. Okay? Very clean. All right. That's what I wanted to say here. It really is a very nice proof. Yes? Yes. Yes, yeah, you're going towards very valid points. Because of course, somehow this object doesn't make much sense if t is larger than k. Oh, sorry, if k is larger than t, because it will be 0. But this is not. This one is not. So indeed, if you want to do this argument very precisely, you have to split this supremum into k's that are larger than t, for which the cancellation doesn't work. But in fact, you only get contributions of this kind. And these we know how to bound explicitly. These are going to be very small. and contributions where k is smaller than t, and then the exact cancellation works. Very good point. You're very sharp. Normally I gloss over this and then nobody notices. More questions? All right. Where did I leave my pointer? Very good. All right, so what more network models can you imagine? Well, basically anything. And anything has been done. Because, you know, networks come around in lots of different places. If you, for example, want to model a collaboration network, for example, amongst mathematicians, you see that you have lots of small cliques. Because in a collaboration network, you connect two mathematicians when they've collaborated on a paper. But if you have a 5-author paper, they're all going to be connected to each other. And you know, all of the models that I've been discussing so far, we will later see, are locally tree-like. Locally, they look like trees. So if you take a vertex, uniformly at random, it's bound not to be in any triangles, let alone 4 cliques, 5 cliques, etc. Now, in a collaboration graph, you are bound to see those. In social networks, typically have those. So there are lots of examples where you think, you know, actually, these models, they're all very nice, but you know, they cannot really describe the thing that I'm looking at, the real-world network that I'm looking at. Okay? So some networks very clearly have a geometry in them. Well, you cannot quite throw that away, right? So lots of adaptations of these models have been investigated, sort of allowing for various other kinds of properties that people observe in real-world networks. And then the game is basically to try to determine their properties. So is there a giant component? What is the degree sequence like? What is clustering like? So clustering means the number of triangles, or the number of triangles for vertices with a given degree, or these kind of things. That's the kind of things that people often measure in real-world networks. Okay? So I'll give some examples. So, for example, the configuration model we will later see has no clustering. If I take a vertex with a vanishing probability, it will be contained in a triangle. Now, for social networks, that's a problem. So you may actually want to add those. And there's nothing from stopping you to generalize the model and not saying that, you know, I'm specifying the degree of a vertex, which is sort of a 2-clique. I'm also going to specify in how many 3 cliques it will be, and in how many 4 cliques, and in how many 5 cliques, etc. And you know, that will give me sort of colored half edges or third triangles or quarter cliques of size 4, and then you just match those uniformly at random. Just in the same way as we've done before. Okay? It becomes much more difficult to analyze, but you can certainly do it. And this is a model that was proposed by Mark Newman and one of his collaborators. Now, as I was saying, there were several papers that were extremely influential. The second paper is this small world model. And that's a model by Mark Newman and Steve Strogatz. And, you know, we have these two phenomena. Scale-free, small world. Scale-free came from Albert Barabasi. Small world came from this. They also called it the small world model. So somehow their idea was that they wanted to explain why in many network models you have very short paths. And short you should think of as being of the order log n or something like that. Now if we start, for example, with a large circle, this is not going to happen. If I take two opposite sides on the circle, they're going to be of the order n away from each other. So we're in bad business. But what they were saying was, now suppose that I would start with this circle, with its nearest neighbor connections and maybe a little bit more, and now I start rewiring a portion of its edges to vertices that are chosen uniformly at random. Just a very small proportion. The statement is that for any small proportion of the edges, you will get a graph that has distances that are of order log n. So somehow the linear behavior is a very bad perturbative point inside this whole spectrum. As soon as you have a few long-range edges, immediately distances drop to log n. So somehow log n is much more characteristic of networks if you have long-range connections than something linear. That was their big invention. Okay, so here is a picture. We could start with something regular, and then as p increases, P being the rewiring probability. You should really think of P as not being terribly large. As soon as you've rewired a linear number of edges, here you already see logarithmic distances. If you rewire everything, then actually you're going to get the GMP for an appropriate P. Okay? So this interpolates somehow with diminishing geometry as you rewire more. It's a clever idea. It's a nice idea. I don't think that they thought of this model as modeling something really. I mean, it was more of a description, just like preferential attachment model is a description for how you can get scale-free degrees. This was more of a description for why you could get small world behavior. On the other hand, the model was taken very seriously, particularly by neuroscientists. So different communities use different models. Epidemiologists use the configuration model. Why? I don't know. Because actually for them it's not a good model, right? If you're thinking about the spread of epidemics, this is happening on a social network. Social network is highly clustered. Configuration model is not. So you're probably going to overestimate the chances of an outbreak of a disease. Somehow the cycles should make it less likely for an epidemic to go viral. Still, that's their model of choice. And this has to do with history. One of the first persons who wrote something about this or read about random graphs probably thought this was a nice model, started working on it, and somehow it stayed within the community. This small world model has been taken by the neuroscientist, and that has created lots of confusion. Because if a neuroscientist talks about small world, they often mean a small world model, not a small world phenomenon. GNP is also a small world, right? We'll see that later on. Configuration model is also a small world. And they're somehow mixing up this notion of what it means to be a small world with somehow the combination of geometry and clustering, etc. Very confusing. But there's lots of confusion, and this always happens when you're working in a field that is multidisciplinary. People view things in a different way, they use different words, and all of a sudden you have no idea what they're talking about, even though they're talking about random graphs. And I always think that then I should be able to understand what they're talking about, but this is not the case. Okay? Physicists talk about soft configuration models, and then I think, what is that? Well, that turns out to be the generalized random graph, for example. So it's just that the terminology they choose is a little different, and that's because their perspective is somewhat different. They think about hard constraints and soft constraints. Hard constraint says the degree has to be equal to something. A soft constraint says the degree has to be on average equal to something. That's precisely the difference between the configuration model and the generalized random graph. Okay? So terminology is confusing. Now here's some more models. Random intersection graph. You start with people and they become part of groups. And then later on, everybody who's in the same group you connect. Somehow a model for classes or maybe even collaboration graphs. Typically models that have highly tunable clustering. If you're part of a group, then this group will give you an entire clique and therefore will give rise to many triangles. Okay? And then there's some spatial models, spatial preferential attachment models, spatial inhomogeneous random graphs, etc., etc. There are lots of them. Actually, that's something that is relatively recent. There are lots of questions out there. We have no idea how these models in general behave, and also how pronounced the geometry really is. So, you know, if you're looking for interesting problems, they're there. Very interesting problems. Okay, this is a model that we've come up with that was trying to strike a balance between, on the one hand, being somewhat realistic, on the other hand, still being analytically tractable. And we called it the hierarchical configuration model. So, as I was saying, the problem with the configuration model is that it has no clustering whatsoever. It has no communities whatsoever. But, you know, if you were to know that there's a set of communities in your network, what you could say is, you know, if I know what the graph structure of these communities is, I only have to connect the different individuals in different communities with respect to one another. So just assume that you know all the communities. One way of doing that is by taking a real-world network, use some sort of a community detection algorithm. The Louvain method seems to be the one of choice, seems to give the best possible answers. This is an ill-posed problem, algorithmically extremely interesting, but very difficult. But basically what you do, sort of as a black box approach, you take a graph, you dump it into the algorithm, it spits out the communities. So it basically says, you know, these certain edges are being predicted by the community structure, and then there's lots of edges that are actually not being predicted by the community structure. Okay? So if you do this on a real-world network, one thing you could do is you could keep these communities, and the other edges, you just wire uniformly at random. That's the configuration model. So now I have a two-level model where I have the small communities that are somehow, I think of as being given, whereas the long-range connections, the inter-community edges, these are rewired uniformly at random. Okay? And you could even think about sort of if you've decided on who the people in the communities are, breaking up the edges and rewiring those uniformly at random. So then you have a two-level configuration model. Every sort of local graph is a small configuration model, but then the connections between the communities are a higher level configuration model. So there's lots of randomness here. There's more randomness here than here if you do this on a real-world network. And of course, in the real configuration model, everything is random. But it's not a good model. Now this is a picture that was taken from a scientific reports paper where we tried this on real-world networks, pretty large real-world networks. So we did precisely what I was describing, computing the community structure, rewiring the edges in the community or not, and rewiring the edges between the communities. Between was always done, inside the communities not always. And then we investigated the behavior of different processes on it. And here I'm showing what happens if you do percolation on it. So think about different epidemic processes. And what you see is that if you do it on the real-world network, you get one curve, that's the blue curve, so that's the truth. And now we're trying to investigate whether this is a good model or not. Okay, which are the models? Well, the simplest thing you could do is just investigate the configuration model. You know precisely what the degrees are, pair everything uniformly at random, and see what happens there. And then the percolation curve looks one way or another. For example, here it's the bottom curve. And here it's this top curve. And here it's this curve. And one of the things you notice is that this pink curve is always very far away from the truth. That's not so strange because the truth typically has way more clustering. So what you see is that the size of the giant component is typically much higher. So that's related to my remark about epidemics, which probably spread on a configuration model quicker than on any other graph. Because somehow the clustering slows it down. But then if you look at these three other models, the data, the hierarchical configuration model where we assume the community structure is just what it is from the real-world graph, and the model where we rewire also the edges inside the communities, in most cases they lie smack on top of each other. Now here, of course, the configuration model is already pretty good, so the other models are identical. But for example, here, it's very difficult to see the difference between this hierarchical configuration model, the hierarchical configuration model with rewiring of the community edges and the data itself. They're really on top of each other. So in a certain sense, we argue that this is a way of describing that somehow on a mesoscopic level, this hierarchy is present, and the configuration model is not a bad model for describing connections between communities. Okay, how you would want to make that a precise mathematical statement is not so clear, but this is a simulation study. The nice thing about this model is that it's analytically tractable. For example, there's going to be a giant component precisely when the configuration model, the original configuration model, has a giant component, because we're assuming that our communities are connected. So somehow the connectivity is determined by the intercommunity edges, not by the within community edges. So it's analytically tractable. That actually makes it nice. All right. So now some more mathematical results about the small world phenomenon. I'll start with some slides about the phase transition. I will not say much about the proofs, because I want to focus a little bit more on the small world phenomenon. This is the result for the phase transition on the configuration model. The first papers are by Molloy and Reed. There's one in 95 and there's one in 98. There's also a beautiful paper by Jansson Wuchak, and I was missing one reference by Bela and Oliver Reardon, which gives a rather nice proof. It's funny because this paper is called A New Approach to the Giant Component Problem, and their rejoinder was an old approach to the giant component problem. But actually their method is fairly flexible in the sense that it not only allows to do it for the configuration model, but also for uniform random graphs, even in the setting where the probability of simplicity is very small, because they prove exponential convergence of tail probabilities, of the probability that the giant component is more than, let's say, epsilon away from this average value. All right, so what does the statement say? Well, it's a bit like with a branching process. There is a critical value, and if somehow your degree distribution is sufficiently large, you're going to see a giant component. If your degree distribution is extremely thin, it has very many vertices of degree 1, actually there's not going to be a giant component, and everything is going to be scattered. And it gives a very precise criterion for when one of the two happens. So you're going to see a giant component. So this always converges, but it could be that the limit is 0, and then it's not so interesting. This converges to a positive limit precisely when a certain parameter is larger than 1, and this parameter is this ratio of expectations. And we'll see later on why this is relevant. This is related, this is a branching process criterion. So you should think of this as being the expected offspring in a branching process is larger than 1. Who does not know about branching processes? Nobody. Okay. So expected offspring larger than 1, then the branching process survives, and actually this probability here can be thought of as the survival probability of an appropriate branching process. And we'll see later on what that branching process is exactly. Okay? Now in the case where tau is in between 2 and 3, this parameter is infinity. Well, infinity is larger than 1, so that means that you're always going to have a giant component. Okay? Now there are some more refined properties known about the size of the giant component, because in the configuration model we can assume all sorts of nice properties. We can say that the minimum degree is at least 2. It sort of says that if I connect to a vertex, there's always a way out. So there's no leaves. So then, I mean, if you have that for a branching process, your survival probability is going to be 1. But then the question is your graph also going to be connected? Turns out that it isn't necessarily. It will be with positive probability, but not with probability converging to 1. Actually, you can write down that if the minimum degree is at least 2, and I'm assuming that there's a positive proportion of vertices that have degree 2, then everything that is not in the giant component is bounded, and that is a random variable, an integer random variable, that actually converges to a non-trivial random variable. That will actually be 0 with positive probability, but it will also be larger than 0 with positive probability. Okay? Yeah? Yes, very good point. I forgot to write that down. Yes. Okay. Then nu is not larger than 2, nor not larger than 1. So I'm always assuming this when there's a giant component. But you're right. There's a very interesting case where all the degrees are 2, and then you see a soup of cycles. And that's a pretty interesting case, and there you see that there's many macroscopic clusters. Good point. Thank you. All right. If the minimum degree is at least 3, then actually it turns out that the configuration model is with high probability connected. And that somehow you can understand, because you know, if you come into a vertex, there's at least 2 further routes out. So it's actually pretty unlikely that that is going to terminate. Right? It sort of seems that everything has at least a binary tree in it, which sort of expands very rapidly. Proving this requires a little bit more effort. Are there any questions about the results? All right. As I said, this is related to branching process approximation. I'll say more about that later on. Okay? Let this be the last slide before we have a small break. I explained on Monday that the generalized random graph and the configuration model are intimately related, in the sense that if you condition the configuration model on simplicity, and in many cases this has a pretty reasonable probability, then you get the same thing as the generalized random graph conditioned on its degrees. So you would believe that somehow if you know the configuration model very well, that you would get the results for the generalized random graph for free. And this is indeed the case. But you should bear in mind that these settings cannot occur. Because in a generalized random graph, we'll always have isolated vertices, positive proportion of them. We always have vertices of degree 1, positive proportion of them. We always have vertices of degree 2. So you will have small isolated things that actually add up to something macroscopic, something linear. So again, here you have a giant component under a certain condition, but this number is always strictly smaller than 1. And it's strictly positive when this is actually larger than 1. And again, this is a branching process computation. And again, when this is infinity, which occurs when tau is in between 2 and 3, this thing is always going to be strictly positive. So this is a special case of let's say, a phase transition in an inhomogeneous random graph. The generalized random graph is an inhomogeneous random graph, but there are way more general versions of inhomogeneous random graphs. And those were analyzed in a very big paper by Bela Bolobash, Svante Jansson, and Oliver Reardon, where they actually proved this statement in humongous generality. Here I'm just focusing on the generalized random graph. All right, so let's have a bit of a break. And then after the break, I'll actually explain what the relation is between this nu, which we see here, and that nu, and argue that they're actually the same.